about it will have heard about Atac at some point. So Atac received his PhD in '91 at Stanford University, where he worked on actually various topics in quantum optics and questions, for instance, of lasing. After a short stay with the fellowship of the National Science Foundation at the Institute for Theoretical Atomic and Molecular Physics at Harvard University, he then became already in '93, I think, assistant professor at UCSB at Santa Barbara, where he continued to work on actually various fields ranging from semiconductor heterostructures, exciton lasers, photonics in cavities, and also continued his seminal work on electromagnetically induced transparency, as actually done here 2 floors downstairs, and actually used very much in context, for instance, of Rydberg physics. Atac then became full professor, I think in '99 at UCSB, and in 2002 received an offer which he accepted from ETH Zürich, where he is since. And there he continues to explore a wide range actually of topics in quantum electronics and photonics. And nowadays also moved, for instance, to exploring these ideas in context of 2-dimensional materials. Atac received a lot of awards and prizes, and I will not be able to name all of them. Let me just mention a few. For instance, the Charles Townes Award of the Optical Society, the Quantum Electronics Award, or also the Wolfgang Paul Award of the Humboldt Foundation. Now, today we are excited to have you here, Atac. It's great that you were able to join us. And Atac will tell us about actually exciting new developments in the context of actually using excitons and photons to explore interesting correlated electronic states and novel 2-dimensional materials. And with this, I want to give you the floor, and we are, of course, very excited to have you here. So let me stop sharing my screen, and now you can probably start.
Thank you very much, Richard. Thank you very much for the invitation. It's a great pleasure and honor to start the colloquium series. And my only the only reason I feel sorry is that I cannot be there personally, because I was really looking forward to discussing with many colleagues. But as you said, Richard, hopefully later in the year, this would be possible. So I'm going to tell you about strong electronic correlations in 2-dimensional semiconductors and how we can probe them using optical methods. And I have a long list of co-workers. 2 of them are in the audience, and 1 of them has just introduced me. But I'd like to highlight the students and postdocs who did the experimental work as well as the theory work. And this is the second part of the talk has been a collaboration with Eugene Demner's group at Harvard. So let me start out with 2D materials. So as I mentioned, that I will focus almost exclusively on 2-dimensional materials. So what makes these interesting? First and foremost, what is interesting here is that we have a more than 6,000 materials, layered materials that can be exfoliated and stacked on top of each other. And these materials, which are sketched in this cartoon from Gorbachev, actually can have very different properties. Some could be interesting for optics, the other could be superconducting, semi-metallic, and what have you. And what is nice is that one can actually, after exfoliation, stack them on top of each other as we used to do when we played Legos, or maybe probably Richard will be playing shortly with his daughter. So I think that this is more or less the same idea in terms of creating something different and sort of novel properties by stacking things on together. So there are many features that makes these interesting. So one of them is that unlike standard semiconductors or standard materials, the screening can be drastically reduced. The the effective mass of the carriers can be heavy. And moreover, we can actually use gates to control the charge density all the way from neutrality to relatively heavy densities of 10 to the 13 or so per square centimeter. So what that means is that we can actually tune the ratio of Coulomb energy to kinetic energy in a region where we have mobile electrons. We can actually start out or even probe regions where the ratio can actually exceed 30. Okay, so moreover, it's not just the different properties of the materials that we are dealing with, but we have other degrees of freedom. And in particular, what many of you, I'm sure, have heard about is that when putting the materials on top, we can actually introduce a small twist angle. And this actually results in very interesting novel properties. It can generate the so-called moire superlattices, and which then exhibit flat bands, even in materials like graphene, where you start out with Dirac electrons. Okay, so before I go on to remind you what can be done with this, I'd like to mention sort of my perspective that what we're dealing with here is really designer strongly correlated materials. So I would really not describe them as quantum simulators, because in the end, what you really are doing is that you're creating a material which can really work as a transistor, as a laser, or as a coherent light source, I should say. So in that sense, it is not just mimicking the properties, but tailoring the properties that is at stake here. Okay, so regarding sort of the possibilities, again, over the last 2 years, there has been an explosive growth of research on twisted bilayer systems, and particularly twisted bilayer graphene. And what makes this system interesting is that it has a very rich phase diagram. As you dope the system, you can go from relatively simple insulating states. I guess this is the band insulator that you obtain either when you heavily electron dope or heavily hole dope. But in between, you have regions where you see superconductivity, and these seem to be tied closely to regions where you see correlated insulator states, mode-like states. And moreover, some of these actually exhibit ferromagnetism and anomalous quantum Hall effect. So there's a long list of papers. So this data is from Dmitry Efetov at ICFO, but the field was pioneered by Pablo Jarillo Herrero. And the idea here again is that as you introduce a twist angle, you change the alignment of the two layers in a way that a triangular lattice is obtained, and this is the superlattice potential that one gets. Now, the question is, given all these interesting states, a natural question is whether it is necessary to have the twisted bilayers in order to be able to explore strong correlations. So to be able to judge that, we should take a step back and consider this. So what if we have a simple two-dimensional semiconductor, as I've sketched here, where we dope, let's say, the conduction band with electrons? So the relevant energy scales would be the kinetic energy that is given by the Fermi energy, which scales with the electron density, and the inter-electron Coulomb repulsion, which scales with the square root of the electron density. And the ratio of these quantities, called the RS parameter, naturally scales inversely with the square root of the electron density. It scales inversely with the dielectric screening, and it's proportional to the effective mass. So if this parameter is small, which is the materials that we are normally used to, then what we have is that the electrons that we inject, assuming that it's a clean enough material, would form a Fermi liquid, right? But if we find a way to reduce the RS parameter, for example, by lowering the density, then there is a long-standing prediction going back to more than 85 years by Eugene Wigner, who suggested that actually one could see a liquid to solid transition, and the electrons at the lowest densities or for strong interactions would form a crystalline structure named after himself. Okay, and so this will then be an example of spontaneous breaking of continuous translation symmetry in 2D, which again is not going to be possible, but for finite systems, we know that one can obtain domains in which one can see the crystalline structure, at least in principle. Right. So this has been actually on the agenda of solid-state physicists, particularly semiconductor physicists, for a long time, and as far as I know, has been in the back of for example, for Klitzing's mind, as well as the colleagues who then pursued and invented fractional quantum Hall effect. So the primary or most of the efforts focused in gallium arsenide, and the problem with gallium arsenide is that this RS parameter is, even at low densities, is on the order of 1. And the reason for that is the effective mass of electrons is very light, which actually makes the electrons have a high mobility, but it reduces the RS parameter, and the screening, dielectric screening, is gigantic. So what the community has primarily focused on is to apply a magnetic field which creates Landau levels with the large separation owing to the light effective mass. And the end result is that one can quench the kinetic energy and confine the electrons into the lowest Landau level. And then in this system, one could expect to get or hope to get signatures of Wigner crystal. And indeed, there have been indications, no proofs, no signature of charge order emerging in the system. But for example, in this relatively old data, one sees that right around the fractional quantum Hall state of 1/5, that there are regions with high resistivity, and this resistance can actually be unpinned, can be removed by applying AC modulation. So the idea here is that the Wigner crystal, because of the inevitable disorder, is pinned, and therefore it's an insulating state. But by applying radiation or modulation at the pinning frequency, one should be able to induce conductivity, and the fact that this picks up at low temperatures is an indication that this could be a Wigner crystal, pin Wigner crystal state. Now, this is kind of, there's a list of, relatively long list of work going back to 30 years, as I mentioned. Now, the two-dimensional semiconductors, like the transition metal dichalcogenides, provide a new angle here. And again, it's mainly due to the two aspects that I mentioned. The first one is that the effective mass is relatively large, and the dielectric screening, due to the HPN layer surrounding it, is relatively low. And one can even dream about suspending two-dimensional materials and taking the dielectric screening down to unity. Okay, so if you put in the numbers, then at similar densities, one could in principle get RS parameters exceeding 40, making this system potentially as an interesting candidate for studying this kind of physics. And what is more, one can also think about applying magnetic field, and because of the heavy mass and the large interactions, in this case, one will not be able to talk about restricting the dynamics into a single Landau level. There would be a large number of Landau levels that will be mixed. And so the question then is, would one in this case obtain integer quantum Hall state or fractional quantum Hall state or Wigner crystal? Will there be a competition between the two? There would be, because at large enough RS, the prediction is that all materials should go into a ferromagnetic Wigner crystal. Okay, and there might be even more interesting states that maybe one could obtain a so-called Hall crystal, which is essentially a system that has a Chern number of 1, but nevertheless, in the case of nu equals 1, but still exhibiting charge order. Okay, so this is then sort of what motivates this talk, particularly the latter part of my talk. But what I will do is, in order to make this hopefully more accessible, I will start out with describing to you optical excitations in charged transition metal dichalcogenide monolayers. So this is the technique that we use in optical spectroscopy, which is relatively new, I would say, at least for investigating strong correlations. And before going on to discuss Wigner crystals, I will also tell you sort of another richness of this material system, which is in a sense the converse of trying to see strong electronic correlations using optics. Here, the idea would be to use electrical control of optical properties, and I'll try to show you or convince you that we can actually realize quantum confined excitons in a PIN junction or NIPIN junction in a monolayer semiconductor. Okay, so now I've already told you about transition metal dichalcogenide. So this is actually a tri-layer system. So it's a layered material, and each strongly coupled layer consists of three triangular lattices where a transition metal layer is sandwiched in between chalcogen atoms. So the list is of transition metal dichalcogenides is also relatively large. The number I do not know, but there are semiconducting ones, superconducting ones, and so on. So now if you take this monolayer, what I refer to as the effective monolayer, and if you look at it from a distance, we see that it looks like a honeycomb lattice where A and B sides are drastically different. So basically on one side, we'll have the transition metal atom, and the other side would be the two chalcogen atoms from the two layers above and below. Okay, so it's a massive graphene-like system. The inversion symmetry is broken, but the Brillouin zone or the reciprocal lattice is again as identical to that of graphene. And basically, in the monolayer level, the interesting physics happens again in the high symmetry points, K and K prime points of the Brillouin zone. Okay, and because of the fact that inversion symmetry is broken, that we expect to see band gaps. And indeed, this is the case, and this is what makes the system interesting from an optical perspective, because the band gap is on the order of 1.5 to 2 electron volts, which make it a perfect match for, say, investigation with optical techniques and high sapphire-based lasers. Now, there are interesting properties here. Again, each valley has, of course, a spin degree of freedom, but because of the large spin-orbit coupling, one can, in principle, and depending on the choice of the material, focus on a single spin transition in each valley. And the time reversal symmetry, in the absence of a magnetic field, ensures that the two transitions are degenerate. And the selection rule for the optical polarization, or the polarization of the optical field, is set by the intercellular motion of the electrons in the two valleys. In one valley, they hop around in a clockwise direction, in the other valley counterclockwise direction, and that basically dictates whether they talk to sigma plus or sigma minus light. Now, for the same reasons that I mentioned, the small effective mass, small weak screening, the absorption spectrum of these materials show very pronounced, strong excitonic resonances with binding energy that is more than an order of magnitude larger than that of gallium arsenide. Actually, without a suspended layer, will have a binding energy that is almost 2 orders of magnitude larger. And basically, because of this strong binding, leading to a small Bohr radius, these have the excitons have very nice properties. For example, if you shine light resonantly on the exciton transition, you can get a very high degree of reflection approaching 90%. So these materials are essentially atomically thick mirrors. And I should highlight here that the pioneering work in this material system was carried out by Tony Hines together with Kin-Fai Mak as his student, and then Shadong Shu. So now, if you want to explore the material, you do so-called photoluminescence, which means that you use a laser to excite electron hole pairs, which relax. And then as they relax, the electron and hole, because of the Coulomb attraction between them, form a bound state. And decay, and this bound state can decay emitting a photon. Because of the strong correlation between electron and the hole, the decay rate can be extremely fast. Now, if there are electrons in the system, then there is another possibility. So the exciton can correlate its motion with an electron and form a molecule, which is an analog of the H- molecule. And this is what we refer to as the trion. And one would also see this, even though its oscillator strength is small in the low electron density limit, one would nevertheless see it in photoluminescence because it does provide the lowest energy state for the optical excitations. Okay, so now I would like to sort of, after this very brief introduction, I'd like to talk about the devices that we use, and these are charge tunable van der Waals heterostructure. So maybe van der Waals heterostructure terminology is a bit of an overkill, because we basically, I will tell you about a monolayer of TMD, in our case molybdenum diselenide, sandwiched in between boron nitride layers. And boron nitride is another 2D material that is insulating. Okay, and then the graphene layers on top and below will act as gate electrodes, which allow us to control the charging of the molybdenum diselenide layer. And here is a micrograph of a typical device that we have. Okay, so now what happens to this system? So basically, the applied voltages allow us to control the charging. And if the material TMD is neutral, that is, it's devoid of free electrons and holes, we see the exciton resonance. This is the color-coded plot, which basically shows how much the reflectance contrast changes. And you can see that this really is of order unity because of this mirror effect that I've told you about. Okay, now the interesting physics happens as we sort of increase the voltage and start doping electrons. And what we then see is that the exciton line shifts to the blue, and there's a new resonance that emerges on the red side and picks up oscillator strength. The same happens if you try to hold dope by reducing the gate voltage. And concurrently, we see that there is a current, a source drain current, that starts to run through the system, again, as a consequence of the presence of electrons for positive voltages and holes for the negative voltages. Now, the new resonance that appears, which actually starts out at the trion energy, is what we describe, borrowing from the atomic physics community, as the attractive polaron. Okay, so to understand this, and this is the only equation that I have in the talk, we can think about a relatively simple system, which is valid at low densities of electrons. So low densities of electrons and even lower densities of excitons. Okay, so what I would like to consider is a system of excitons and electrons and a density-density interaction between them. But because of the low density of electrons, I would make the rigid exciton assumption, saying that even though electrons are present, the exciton interacts with electrons as a rigid object, much like two atoms interact with each other without really us having to worry about, oh, in the presence of the other atom, the eigenstates have to be superimposed, etc. So these we do not need to consider. We will take as an assumption again that the exciton remains in its 1s state and has an effective contact interaction with the electrons. And this interaction strength is determined by the binding energy of the molecular state. Now, again, I think for many of you, this is, I assume it's well known. So we followed up on what was done in cold atom community. We adopted the Chevy ansatz to say that we can find approximate eigenstates of the system in a truncated Hilbert space, where we can write the wave function as a superposition of a bare exciton and an exciton that within a Fermi C electron hole pair. Okay, hole here refers to a hole in the Fermi C, not a valence band hole. And such eigenstates in this form can be thought of as a coherent superposition of a bare exciton and collective excitation of many trions in the system, okay? And basically, it is the bare exciton part or the quasi-particle weight that is responsible for the strong oscillator strength of the attractive polaron. Now, back to another device in this case. So what I would like to emphasize here is that the attractive polaron lines can be extremely narrow, even narrower than the exciton. So that is really a very nice demonstration that even though we have electrons in the system, the main effect is the renormalization of the energies or creation of new resonances rather than line broadening due to incoherent scattering. Okay, but the more important effect for this talk is that even though attractive polaron has a non-trivial and relatively weak dependence energy, in the electron density, the repulsive polaron shifts very abruptly as we change the electron density. And this provides a fantastic tool to monitor what is happening to the electronic system. Okay, so before I do that, you could also wonder, so how do we determine? We put in electrons and we need to find out electron density. How do we determine this? So one possibility is to treat the system as a parallel plate capacitor. Once you have charges in the TMD, you can say that, okay, now I have two quasi-metallic layers and the capacitance, geometric capacitance should determine the electron density as a function of the voltage, which works quite well. But there is a more elegant way of demonstrating it, and that is to look at exciton polarons at very high magnetic fields. And what you see, for example, here, that this polaron spectrum shows these cusps where the energy shifts to the blue and the line width of the exciton narrows down, okay? And these are separated by exactly the degeneracy of a Landau level. So that basically by looking at the gate voltage and also confirming the linearity of the separation of these sort of successive Landau level fillings with the gate voltage, we can not only determine the electron density, but also make sure that we can use the gate voltage as a nice and direct probe of the electron density in the system. Okay, and here you see the different Landau levels, and we call this Shubnikov-de Haas oscillations in optical conductivity in analogy with the standard method that is used in low frequency transport. Okay, now that was my introduction. So now I would like to tell you about recent results on how to control optical properties beyond these polaron shifts using electric fields. So the device that we have is the most complex one we have fabricated, which looks a lot like the device that you would see from mesoscopic physics transport communities. So it has multiple gates, source and drain, and right in the middle, there is this constriction. So there is a top gate that is about 200 nanometers thick and separated by about 100 nanometers, okay? So, and then underneath is a molybdenum diselenide layer and two HPNs. In this case, though, instead of graphene, we have gold gates in the structure, which actually reduces the quality a bit, but not in a dramatic way, okay? So such a device actually is a quantum point contact-like device. So when we basically, by changing the gate voltage, we can actually make sure that the carriers in this constriction can be depleted out. And that's what you see here. And then normally this is a device in which you will see quantized conductance plateaus. We see just the first rise, the second plateaus, well, would require some imagination, but this was the first try, and this is not exactly what we are after in this device. Okay, so but just to show you that electrical gates work, and then we can measure actually also conductivity of the material. Okay, now our focus is, of course, on optics. So this is the analog of the measurements I have shown you before. You see some problems that for example, hole doping is very non-trivial. So it increases abruptly and then levels off. So this is a generic problem with molybdenum-based materials where the P contact doesn't simply work very well. So if you look at the electron side, it's better. The lines are broader. And what I would like to do is to focus on this 5-volt backgate voltage, where basically most of the material is heavily electron doped, as you can see from the presence of the attractive polaron line and the relatively large blue shift of the repulsive polaron. So now the question is, we take this device at 5 volts backgate, and we're going to apply a voltage on the top gate and start reducing this top gate voltage. Now, what we would expect is that as we make this top gate voltage more negative, such that it's more negative than 5 volts, so it's less than minus 5 volts, then we will start doping the material underneath the top gate with holes. So most of the monolayer is electron doped, so we have these n-doped regions, but right under the top gate, we're going to have hole doping, okay? And in between, there is necessarily an undoped neutral region, and it is in this neutral region that we can have bare excitons, right? Now, but these bare excitons actually are subject to relatively large in-plane field of order 0.1 nanowatts, 0.1 volts per nanometer, sorry. And what that means is that these large fields create a large DC Stark effect and redshift the exciton energy such that one can have a trap for excitons precisely in this relatively narrow, on the order of 10 nanometer, undoped region separating the electron and hole doped regions. Okay, and this is precisely what we see. So if you look at it here, so if we start out with the top gate at 0 volts, we don't see anything because this is basically electron doped. There is no resonance here. As we reduce it, then we start to see that we compensate for the electron doping and then and therefore reduce the electron doping because of the top gate voltage. So we go back to the exciton level, and as we decrease it further, we see that on the one hand, there is a region where we have the whole repulsive polaron, but there are additional lines, many discrete lines that are much more narrower, about a factor of 10, 20 narrower than the exciton line. And they shift initially abruptly and then slowing down. And we believe that these are essentially quantized, one-dimensional excitonic states that exist only in the region in between the two layers. Okay, so it's really remarkable that this confinement is in large part, particularly for these lower energy states, is due to the DC Stark effect. But you can see that there are even confined states with higher energy than the exciton, and we believe that this is due to the fact that the repulsive polaron formation in N and P doped regions essentially allow or contribute to confining the excitons in the undoped region. Okay, so I find this remarkable because this is a PIN device, right? And it has a very tiny undoped region, and there we have one-dimensional excitons with quantization of their motion along the electric field direction. Now, how do we prove this? We look at the polarization properties, okay? So basically in two different regions. So in this case, these gray areas are the top gate voltages. So if our focus laser spot is overlapping here, then basically these lowest energy resonances are all linearly polarized along the same axis. And this is precisely what you expect to see from a 1D emitter due to the electron-hole exchange interaction. And it is well known for example, for carbon nanotubes that the emission is always polarized along the axis of the 1D wire. If you go to this gap region, we have two kinds of wires, right? So one is essentially along this long edge, and one is along the short edge. And then consequently, we see polarization of both types, and showing us that even in this 200 nanometer region, we actually have confined excitonic states. Okay, so this I find, as I said, exciting because we can actually create quantized excitonic states. This is really interesting for realizing strongly interacting photons because normally, or what has been discussed up until now, is either zero-dimensional emitters like a single atom in a cavity or quantum dot in a cavity or NV center in a cavity as a nonlinear photonic system. And our community with polaritons actually have been pursuing two-dimensional polaritons and try to use interactions between them as a platform for enhancing or creating strongly interacting photons. So what we are seeing is now there is probably a better intermediate way. If you have 1D excitons, the interaction is dramatically enhanced as compared to 2D excitons because the only, let's say, extended direction, there's only one extended direction, which increases the probability of overlap of the excitons dramatically. And yet, unlike 0D emitters, the oscillator strength coupling to the cavities is still strong, that we expect to be able to see polaritons, particularly given that 2D excitons in this system show normal mode splittings exceeding 30 megaelectron volts. Okay, and of course, one could also extend the top gate or modify the top gate that one can make quantum dots and actually an array of quantum dots, array of wires. So basically, all the aspects of electrical control will be at our disposal in this system. Okay, so now back to the main topic. So the question now is, how does the electronic state modify the exciton polariton dispersion at a zero magnetic field? So previously what I showed you is that indeed, here you see that whenever we have electrons, the energy of the excitons are modified, okay? So, so this is the starting point. If you have an undoped system, we have an excitonic dispersion. So what I'm plotting here is exciton dispersion. Maybe what is not so familiar is that the exciton dispersion, actually, because of the electron-hole exchange interaction, is rather non-trivial outside the light cone. So basically, I neglect the light cone here because it exists over a very small momentum. Outside the light cone, there is a large longitudinal transverse splitting that can be traced or understood as the long-range electron-hole exchange interaction. And basically, the splitting of the two scales linearly with momentum because of the longitudinal branch scaling with linearly with momentum. And these are normally not observed because the momentum where this is relevant is outside the light cone, and therefore we do not have optical probes normally to see these features. Okay, so this is nevertheless, so we normally look at this k equals 0, but this is the exciton dispersion of an undoped system. Now, if you put the electrons, like I have shown you before, and if the electrons are in some liquid state or disordered state, then what we see is a blue shift due to the repulsive polaron formation, right? So basically, I'm assuming a constant density, so I move in this plot that I've shown you before. There is a blue shift, maybe some line broadening, but then otherwise the dispersion remains the same. Now, if we, on the other hand, if these electrons form a crystalline state, a Wigner crystal state, then something else happens. And the reason for that is that now the excitons that interact with electrons see a periodic potential, and they backscatter of the electrons of this periodic potential, and that defines a new reduced Brillouin zone, and where the bands fold and lead to new resonances at zero momentum or within the light cone. Okay, so therefore we have a possibility to see additional resonances because of the crystalline state of that are predominantly high momentum in character. And these momenta could be basically 2 orders of magnitude larger than the optical momentum. And yet, because of the Bragg scattering or umklapp scattering, we will be able to have new resonances at k equals 0. So the actual band structure, so this is a sketch, was analyzed by Clemens And basically, this is how it looks like. So the assumption here is actually a relatively sort of simple approximation. We basically, or what Clement said, is that let's neglect the dynamical degrees of freedom of electrons. Let's assume that electrons have a certain density distribution. We neglect the fluctuations. Okay, and then it's a density-density interaction. So basically, there is a sort of a Hartree term, an effective potential, periodic potential, this leading to a modification of the exciton energy. And this results in the band structure shown here. And this yellow area is the light cone. So this is the region or the momenta of excitons which can really decay by emitting a photon. And this is normally what we see. Again, actually, this dispersion exists only outside the light cone, but let's leave this aside. But the main point is that there's a new resonance that picks up an oscillator strength because of its mixing with the true K equals 0 excitons. Okay, so that's basically what we would expect to see. So let's see what happens. So this is the yet another sample showing the repulsive polaron and attractive polaron at zero magnetic field as we electron dome. Okay, so what we will do is that we will focus in this region of low electron density up to 3 times 10 to the 11. And what we will also do is that we will differentiate the signal with respect to voltage. And then we see that there is a peak that appears on the blue side of the exciton, and that shifts as we increase the electron density. If we monitor the density dependence, we find that it falls on a line that is determined by an exciton mass of 1.1, which is a bit smaller, but within the error margin of our experiments, agreeing with the center of mass of the exciton and consistent with the triangular lattice. Okay, so that is good. So then the next thing we did is we wanted to look at the temperature dependence. So this measurement was taken at 80 millikelvin, where the feature is relatively well developed. As we go to 4 Kelvin, we can still discern the umklapp peak, but presumably because of the thermal fluctuations, the electrons are not as well confined and the lines are broader and weaker. And as we increase the temperature further, above 10 Kelvin, you can see that the peak is completely gone. We have a thermal melting of the Wigner crystal at a temperature between 10 and 16 Kelvin. Now, because of the at least partial quenching of kinetic energy, the signatures become more robust at finite magnetic fields. So this is at 6 Tesla for 2 different polarizations. And you can see that particularly for sigma minus polarization, now the umklapp peak is quite strong. And part of this is that not that this polarization is expected to be stronger, but basically the energy detuning between the sigma minus umklapp peak and the sigma minus K equals 0 peak is smaller than that of sigma plus. And this is precisely, again, due to the electron-hole exchange interaction, so which basically makes sure that the excitons at large momenta, they do not see the magnetic field to first order. They are linearly polarized, they mix the two values, and therefore upon umklapp scattering, the splitting between the two is going to be very small. Whereas the K equals 0 excitons are subject to Valley-Zeeman effect, which leads to a sizable splitting of on the order of a milli-electron volt. And this in turn basically means that the sigma minus can mix much better with the K equals 0 as compared to the sigma plus, and this is the difference that we see here. Now, and this is also what we see that as in the presence of a magnetic field, there is a Zeeman splitting of the main exciton peak, but the umklapp resonances. There is some splitting, but this is all within the error margin, and actually it would be interesting to understand the nature and the strength of this. So another point is that well, since the features are enhanced when the two resonances are close to each other. We can ask the question, can we actually anti-cross the k equals 0 resonance with the umklapp resonance? Because basically one doesn't, the umklapp resonance doesn't depend on magnetic field, but the sigma minus resonance does. So we can, in principle, by increasing the magnetic field, may start out for a given electron density, a situation where the resonance is above the umklapp. And in this case, we would expect to be able to see the resonance more strongly. And indeed, as you can see at 14 Tesla, one can even see in bare data the new resonance appearing and merging with the bare exciton resonance. And so this is basically nice news. Then we see that on the higher energy side, though, higher density side, that we lose the umklapp peak. So basically, we believe tentatively what is happening is quantum melting. So at these densities, the system is no longer in a Wigner crystal state. And something else happens at nu equals 1. And this resonance at nu equals 1, we believe, is due to the fact that now we have an integer quantum Hall state, which has softened magnetorotons. And it is these magnetorotons that also lead to broad features in optical spectroscopy. These are different than umklapp. So umklapp in an ideal system without disorder, which of course doesn't exist, would lead to delta function resonances, whereas the dressing of excitons by magnetorotons would result in broad resonances due to Van Hove singularities at the roton minimum. Okay, so much more has to be done. We need to look at higher quality samples, hopefully correlate with transport measurements, but we believe that what we see here is really the first direct evidence for the charge order that appears in a Wigner crystal, where we do not have an external potential and the crystallization occurs spontaneously. Okay, so I already made the first point. So actually, I made all the points. So one interesting question is, of course, spin physics. So how can we use this relatively insensitive umklapp resonance to say more about the spin physics? Because one of the more interesting questions in Wigner crystal is the spin order, whether or under which conditions one sees non-trivial spin physics at very high interactions. As I said, the prediction is that it's going to be ferromagnetic, but as one lowers RS, then we expect to reach a regime where one could actually even change the crystalline structure and have anti-ferromagnetic correlations. Okay, I'll stop here and thank you for your attention.
Thank you very much, Atac, and maybe at least the panelists can actually unmute themselves to actually give Atac a round of applause. So thank you very much, Atac. I'm sure we have a couple of questions. So there are several ways you can do this. There's a Q&A window where everybody can type questions, or as Alex Högel is doing right now, just raise your hands and I will unmute you. So we have a question from Alex. Alex, give me a second and keep your hand raised so that I can see you. Okay, excellent. You should be able to talk. Yeah.
Okay. Hi, Atac.
Hi, Alex.
It was a very dense talk. Thank you for the beautiful physics. I have a question related to the last part. What is the lattice constant of the Wigner crystal and what determines this?
Yeah, so the lattice constant is directly determined by the density, right? So because we have a certain density of electrons that basically sort of form a crystalline structure to minimize their Coulomb repulsion. And as we change the density, the lattice constant is changing. And in our case, this is ranging, if I remember correctly, between 30 and 10 nanometers.
And according to your explanation, it has nothing to do with any potential Moiré superlattice imprinted by HBN encapsulation?
We're almost absolutely sure about this because basically the HBN and TMD lattice constants are so different that any Moiré potential would have a periodicity on the order of 1 or 2 nanometers. So I think we can really exclude that. I mean, more interesting possibilities could be that if our graphene contacts were closer, then the alignment of HBN and graphene could introduce a Moiré potential, which can then be sensed by excitons. Actually, Kim Fein-Mak and Jishan had an experiment like that, but in that case, I believe the graphene layer is only a nanometer or so away, whereas in our case, this is 70 nanometers. So in that sense, I mean, these length scales are completely inconsistent with any alignment or any angle well, you don't need an angle actually because of the lattice mismatch. Mm-hmm. You will have a very short Moiré periodicity between HBN and TMD.
Thank you.
We have one more question from Jan van Delft. Let me see. Jan, you should now be able to unmute yourself and use the chat. Yeah.
Hi, Atac. Good to see you again. So I was wondering what would happen if you increase electron density. You seem to have focused on the regime of low density. So is it conceivable to go into that regime also, study more strong correlation effects?
Well, I mean, basically, as we increase the electron density, in our system at least, we seem to lose the umklapp peak. Now, again, even though we increase the interactions at higher densities, the RS parameter is becoming smaller, right? So the kinetic energy is becoming more important. And so it is actually expected that at higher densities, the Wigner crystal would destabilize. And we, again, as I said, tentatively argue that this is what happens here. And we even have a Hartree-Fock phase diagram, I mean, for all its merits and shortcomings, which says that for low densities, let's say low magnetic fields in this case is better, but also in this axis, it's going to be density. Low density prefers Wigner crystal. And as you increase it, then you have competing states. Normally, without a magnetic field, these would be the melted Fermi liquid state in the presence of a magnetic field, sorry. This would be the integer quantum Mole state, and potentially in clean samples, also fractional quantum Mole states. So we learn now that for example, so initially I thought that with such large values of Coulomb to cyclotron energy of 20 or so, one would not obtain fractional quantum Mole states. But whereas we learned from Mansour Shaigan that actually up to ratios of 15, nucleus 1/3 can survive. So some of these quantum Mole states, and particularly the 1/3 state, can be very robust. So in principle, the diagram is very rich to be, I mean, if we have a clean system, I think we will have very interesting features as we move up and go through these liquid to crystal, liquid to solid transitions at fractions where the liquid state is very robust.
Okay, thank you.
Do we have more questions? If not, let me ask actually two. Number one, in the optical absorption response, do you think at some point you could even see collective excitations of the Wigner crystal, basically the phonon spectrum?
Yeah, so that is, of course, the other sort of interesting direction, particularly, let's say, from a polaron physics perspective. So the question is, sort of what exactly determines, if I move back, what exactly determines the energy of these resonances, right? That we see. I'm sorry about that. Yeah. So here I sketch what Clemens, or this is Clemens' sketch actually, showing the spectrum with this mean field approximation. In principle, of course, that if you take into account the fluctuations in the electronic degree of freedom, we're going to have a Bose-Polaron problem. All right, that the excitons can actually be dressed by collective excitations out of the Wigner crystal, and this will in turn result in a modified spectrum. And this is on the agenda. I think this is an interesting direction. The only maybe sort of, you can say, hesitation or reason for being humble is if you look at our spectrum at this point, it is not clear if we can see any of these finer predictions with the samples that we have. So we definitely have to improve the sample quality to be able to go into this finer physics.
Mm-hmm. Thank you. I think, is that correct, Alex? You have another question.
Yes, I have one related now to quantum wires. Good to see one dimension being back. So do you expect then a charge valley separation instead of, a valley charge separation instead of spin charge separation in these 1D quantum wires?
Yeah, that's an interesting question. So I don't know. I think it would be definitely sort of interesting to see and explore this regime. So I mean, of course, even though lifetime of these excitons are longer based on the line widths, I mean, we measure line widths as narrow as 0.1, 0.2 milli-electron volts, right, which is almost unheard of for TMDs. So the lifetime has been prolonged, and that's something you would expect because this collective enhancement effect is suppressed. But still, it's a short lifetime. So the question is, what is I mean, there is, on the one hand, we expect interactions to be strong, but excitons are dissipative. So what exactly does this mean for predictions based on for 1D physics? So so that, I think, is there definitely is interesting physics that is out there. And we can also think about, actually, particularly in this gap region, we can have 1D excitons separated from a 1D channel of electrons. Okay, so, and in that way, we can actually also think about probing the Luttinger liquid states using excitons that are in the immediate neighborhood. So the possibility seems to be very rich, but our focus now is on photon correlation. So we want to see if indeed 1D enhances the interaction strong enough that we could actually see anti-bunching in this system.
This is very exotic. Thank you.
So actually, I would also have a question regarding this sample. So do you have some ideas how one could probe conventional 1D physics in these systems? Essentially, like a structure factor or something like this, because that would have very peculiar properties for the Dong-Schledo gas, for instance, right?
Yeah, so I think that in terms of the structure factor of the electrons, I'm not, if you have 1D electrons, this I'm not sure, but basically for excitons, if this is photon correlations, I would say. So the question is whether we have enough resolution, and we don't, right? So in our system, but one can dream. I mean, in your immediate neighborhood, there is AtoCube with NeaSpec devices which allow for very high spatial resolution, and then one might dream about measuring density correlations in the system.
Mm-hmm. Or even, yeah, I see.
But maybe there's a smarter way of seeing this that's also possible.
So do we have more questions from our attendees? Atac, let me ask you just one thing also about this. Two things. Number one, you said increased interactions, that's just a one-dimensional effect, but your excitons will also have now a permanent dipole moment that also increases interactions again, I guess.
Yeah, so this one, I think it would contribute to enhancement of interactions, but we haven't estimated sort of how dramatic it would be. I mean, basically, the size of the dipole would still not be terribly large. And roughly what we know from dipolar excitons in gallium arsenide, that the enhancement of interaction, if the dipole size is comparable to the Bohr radius, then you get about a factor of 5 to 10 enhancement. So it would contribute, but I don't know if it will be 10% or factor of 5. Honestly, I don't know the numbers. But I think that just sort of the overlap arguments should already put us in, and given the line widths, should give us some degree of anti-bunching. But maybe I'm being too optimistic. We should see.
And do you think one can thermalize these excitons so that you are actually getting closer to the ground state?
Yeah, I think in principle, I mean, these experiments are reflection experiments, right, with white light. So basically, we do not really create a high density of excitons and look for how they relax and form a thermal state or non-thermal state. In principle, yes, you know, that once the density is high enough, the thermalization time due to interactions will take over the decay. Of course, there are uncertainties, you know, that maybe Auger will take over before and not allow for true thermalization. It's hard to say, right? But let me say that one interesting aspect of this PIN device is that in principle, one actually can avoid optical doping, because I can actually think about applying a voltage between the P and N doped regions, kind of a source drain type voltage. And in this case, I would be able to increase the Fermi energy difference between the two layers to about an exciton energy, or one of these 1D exciton energies. And then at this point, one should obtain an electrically injected excitonic condensate. And again, assuming that the temperature is low enough and disorder is low enough, then that could actually be a way of getting a coherent light source.
Cool, thank you very much. If you don't have any further questions, I would say let's collectively thank Atac again for his really beautiful talk. Thank you very much, and yeah, with me presentative manner. And I think you will actually be now also meeting some of our students from MCQST in the next couple of hours. So also actually great that you took your time for that, or take your time for that. And yeah, I think this brings this session at least to an end. I think that Barbara thought she can guide you through the further process, and also maybe the corresponding students that they know where to meet you in the virtual world here in this in this venue. So thank you very much, Atac.
Thank you. Bye. Have a nice day.
Thank you. Thank you very much. So yeah, for all the people who have one-on-one meetings with you, it's in the round table, which is in Meet Anyway below.
Leave this one now and then join the round table, right?
Exactly. In about 15 minutes.
15 minutes. Okay.
Before.
Sounds good. Okay. Bye then.
Bye-bye.
Bye.